Okay, so welcome back everybody to the afternoon session of this wonderful workshop. So our first speaker of this session is Francesco Sorge, who will tell us about high-frequency gravitational waves in electromagnetic waveguides. So please go ahead.
Well, thank you very much for giving me the opportunity to be here today. This is a very interesting workshop, and I'm very happy to be here today. As you can see for the title, my short talk will be about the interaction between high-frequency gravitational waves in electromagnetic waveguides. And this is the motivation. I think that I can skip the motivation because I believe that all of you are well motivated since you are here today. And so let me go to the content. That it is. So what we want to do is to explore possible nonlinear effects arising from the interaction between a very high frequency gravitational wave and the electromagnetic wave in a waveguide. The idea is to show the existence of a second harmonic generation effect similar to that which we know in nonlinear optics. And unfortunately, as we will see, this is a very, very small effect. So the possibility of an experimental observation is probably a distant dream. Okay, this is the outline. We will recall briefly the TE and zero modes in a rectangular guide. Then we specialize the result to the gravitational wave background. And then we will focus on second harmonic generation, and then we will draw some conclusions. Okay, this is a sketch of the transverse electric and the transverse magnetic modes in a rectangular waveguide. We will mainly focus on. Pardon. Okay. Go back. This is okay. We will focus on the electric 0-1 modes like this. Okay, this is the fundamental mode which is usually employed in the transmission in a rectangular waveguide. And what we can do is to solve the Maxwell equation with the required boundary condition. This is the sketch of a rectangular waveguide. There are the dimensions A and B along the X and Y axis, Z the direction propagation of the wave inside the guide. And then for the transverse electron modes, the solution of the Maxwell equation are like this. We have non-null components for the magnetic field along the X and Z direction, and the electric field is only along the Y direction. Kz is the wave vector along the Z direction, and the omega c is the cutoff frequency for the fundamental mode. A zero represents the electromagnetic fields in a flat background, that is when we have no gravitational wave background. Now, how things change if we consider a gravitational wave? We know gravitational wave come with two polarization states, plus and cross, but for simplicity, here we assume a single polarization state, that is the plus state. Also, we will employ the TT gauge. If there is time, we discuss about this choice. And so the line element is like this. We also assume a waveform like this. H is the gravitational strain, and in this case, we go to solve the Maxwell equation using an orthonormal tetrad like this. You can easily check that such a tetrad is a Fermi-Walker transporter, so that it is the best approximation to an inertial reference frame in a curved space ground. In this case, the Maxwell equation to the lowest order are like this. The covariant derivatives can be replaced by the ordinary ones. And we project the Faraday tensor onto the tetrad in such a way. And also we assume a pre-existing electromagnetic TE10 mode, the fundamental mode inside the cavity, the guide. Okay. To the lowest order, we expect that the gravitational wave will excite only modes involving the X, B, Y, and BZ component, and so we decompose the field, the electric field and the magnetic field in such a way. This is the background electric and magnetic fields, and then these are the gravitational induced perturbation. We use the Maxwell equation, and you obtain this set of differential equations. Now, if we put all things together, we get these three inhomogeneous wave equations that represent the evolution equation for the electromagnetic perturbation in the presence of a gravitational wave. Now, if we take the first one here, and we assume the case of a very high gravitational wave, very high frequency gravitational wave, having the same frequency of the electromagnetic TE10 mode, then we can solve perturbatively the equation, assuming a form like this, where the function A is a slowly varying function of Z, and kz prime is defined as you can see this, and this is the cutoff frequency. We neglect the second order derivative, and we obtain the following expression for the function A. L is the length of the waveguide. At this point, we can evaluate the function Az at the end of the guide, and we get the following result, where delta K is the mismatch vector. Okay, represent the main cause of the attenuation of the effect we are looking for. If we combine the background electric field and the correction due to the gravitational wave, we get the following total electric field at the end of the guide. And you can see we have two contributions. This is the background mode, and all this is the gravitational wave induced the electromagnetic perturbation. The key point is that the frequency of the perturbation is twice the frequency of the original electromagnetic field. A similar result you can find discussing the X component of the magnetic field. Again, we have a frequency which is doubled with respect to the frequency of the electromagnetic field in the guide before the gravitational perturbation. This is an example of nonlinear effect induced by the very high frequency gravitational wave on the electromagnetic wave inside the waveguide. We move to the evaluation of the contribution to the Poynting vector. We use a general definition for the time average, and in the present case, the contribution due to the second harmonic is like this. Okay, and you can see that is a second order correction in the strain. Well, we can evaluate the power carried by the second harmonic at the end of the guide, integrating all over the section of the guide, and then we can evaluate the photon flux. That is the number of photons created with frequency 2f. F is the initial frequency of the fundamental mode. Okay, this is the flux. We point out that it is not possible in general to make delta K is equal to 0. I call this a match. And Here I report a numerical example. So for example, if you take a gravitational wave at 10 gigahertz and a waveguide WR102 whose parameters are like this, and we take an electromagnetic field inside the guide of 3 millitesla, then in standard international units we get the following result. Delta phi is like this, so that we get the maximum flux value as a function of the strain, which is obtained for an optimal waveguide length, which is 0.5 meters. And it is interesting to compare with the black body noise from the cavity. If we assume a cryogenic temperature operation of 4 Kelvin and then detection bandwidth of about 100 kilohertz, the background in number of photons of the background is about 77 times 10 to the minus 3 photons. And if we want to detect a number of photons at least equal to the noise background, we need an integration time which is like this. And for example, if you assume an integration time of what is of 1 hour, the gravitational strain threshold is about 10 to the minus 17, which is no good because we are considering a gravitational wave with a frequency which is of the order of gigahertz. Probably such gravitational wave, if existing, have a strain which is about 10 to the minus 30 or so. And it might be that the sensitivity could be improved using a Fabry Perot resonator with a finesse, a very high finesse, but as you can see, we are again by far from the value, the interesting value for such a type of gravitational waves. And so here are the conclusions. An interesting feature or defect is that the produced photons have a frequency which is twice the frequency that the photons originally propagating in the waveguide. This is interesting because it could be easy to discriminate such photons. Unfortunately, also assuming optimistic values of the involved parameters, the number of such photons is very, very small. It might be that an high finesse Fabry-Perot cavity can give us some amplification, but in any case, we have only a very, very small number of photons to be detected. In any case, the effect seems interesting in its own right because it is a non-trivial example of a nonlinear interaction between quantum fields and very high frequency gravitational waves. And finally, this also suggests that any promising route towards a quantum theory of gravity probably will need to face high frequency gravitational waves for searching for gravitons evidence. Okay. And this is all. And thank you very much.
Okay, thank you very much for this nice presentation. So we have time for a few questions now. I see one all the way in the back. Yeah, can you use the microphone, please? You have to press the button. Yes.
It doesn't work. Yeah.
Hi, yeah, that's good now. Okay, thanks for the talk. Maybe you said it and I missed it, but when you give the number of photons at like the derivative of the number of photons as a function of time, I didn't see any time units, and I was wondering, because the h you give, I think, is dimensionless, so I was wondering if you can go back a few slides.
You can...
This one here, yeah, with your red formula. I was wondering what is the typical time unit here?
And here, sorry. Here,
On the red one, or then in the slides afterwards. Maybe you said it, but
this is photons for second.
okay. This is second. I was just wondering if it was
Yes.
because after you said time an hour and okay, thank you.
As an aside, yesterday, for example, Aldo discussed about heterodyne detection. It may be that there is a possibility to detect such a tiny flux of photons using some similar technology, because the real problem is that the effect is a second order in the amplitude of the gravitational wave. And I don't know if it is possible to match such a signal with a local oscillator to get a signal which is proportional to the amplitude and not to the second power of the amplitude.
So you said that there is a background field, isn't it? That background field is a static field?
The background field is zero. In the electromagnetic guide, there is a propagating electromagnetic wave.
Should be a linear term with that background field, I guess. Maybe you have to look that one as well instead of quadratic term.
And the other problem it is related to the TT gauge we are used.
So there's another question in the back.
Yeah, I think I didn't understand why it's why is it a second harmonic? Can you explain again why the gravitational wave signal does the second frequency, 2 omega?
The gravitational wave acts as a nonlinear medium, as in nonlinear optics. So there is an interaction, a nonlinear interaction, a nonlinear coupling between photons and the gravitons inside the guide, and the result is a tiny flux of photons which propagate along the guide with a frequency which is doubled with respect to the original frequency of the electromagnetic wave.
And this is completely independent of the gravitational wave frequency then?
It seems it is so, because you can see here there is a frequency, but the similar frequencies are also inside, you can see here, this term. This is not, here we have the frequency, F is the frequency of the gravitational wave and also of the background electromagnetic wave. And it depends on the frequency through this quantity, because note that delta V is given in like this fraction. Here we have the frequency. The frequency is to the square here, and you have a simplification here, but there is a residual dependence on the frequency here. So the result should depend on the frequency of the gravitational wave or on the frequency of the background electromagnetic field.
Okay, I think there are a bunch of more questions. I would take Joachim, and then in the back, and then here.
Has anyone ever studied this not for microwave waveguides, but for optical waveguides or fibers? Because the same effect should exist there, right?
It might be, but not with a relation to gravitational wave, as far as I know.
I mean, I see here some powers of frequency in the denominator. So maybe if one goes to higher frequencies,
yes,
it gets harder.
It is very similar to the result in nonlinear optics. Basically, it is the same, but in nonlinear optics, we have two photons. We are coupled by a nonlinear medium, a crystal, for example. Here, the crystal is replaced by the gravitational background. This is.
Okay, so once in the back, and then you. Sorry.
That was related to my question. So If I wanted to do second harmonic generation, I would use a nonlinear crystal, which might have a chi square or chi 3 nonlinearity or something. And so second harmonic generation, I think chi 2. So you should be able to characterize that like a crystal parameter and sort of compare. So someone who, like me, would want to know what's that effective parameter, like you do get in a crystal.
I think it is not exactly the same because in optics there is an effect which is mediated by the crystal, the polarization, which is not linear inside the crystal. In this case, the effect has a different origin. It is due to the interaction with the gravitation.
Yeah, but you should be able to get you should be able to describe the nonlinearity like you do in a crystal to give a certain parameter which tells you, because when I have that nonlinearity, it will also create, you get a broader effect around broader than the line width of the resonator as well. I just think that could be done. That was just.
I have not to consider such aspect.
Okay, maybe one last question, and
just a quick question: is there any reason why the magnetic field is so small?
Thank you. I also wanted to ask.
It's due to the dimension of the waveguide, I guess. You can't. How big is this waveguide?
In this example, these are the dimensions.
Yeah, but the B0 is like 3 millitesla. You have superconducting.
We are at the limit of the magnetic field. We can be used in such a waveguide.
Okay.
This is the maximum value.
That's the maximum value. Okay.
I think.
Thank you.
Okay, thanks very much. So as a reminder, after these talks, there will be more time for discussion. So if you have more questions for Francesco, you can ask him then. So let's thank him once more.
Thank you very much.